V.
Thank you all for coming today. We really appreciate you guys coming out for this. So I don't know if you guys are familiar with kind of what today is. It's the Eaton Design Excellence Award, and it recognizes and encourages students, recent alumni, and the faculty that inspire them to pursue excellence in design and to impact economic development in the Midwest and beyond. This year, the award was, ECE faculty determine the winner. So each year we have, if you've graduated in the past 5 years, including grad students, you can submit your original design work, and that gets reviewed, and then you can win this award. And this year we have Markell Baldwin from Tesla, so he's going to introduce him, or I guess I'll introduce him, sorry. He has a bachelor's degree in electrical engineering from 2014, and he is a senior engineer for Tesla Motors. So Markell?
Thank you. All right, what's up guys? Let me log into my computer and walk you guys through some of my stuff. So like Brooke said, I've been at Tesla for like 5 years actually. I started off as an associate engineer, and I'm actually gonna walk you through most of this stuff. So let me just display it as I walk you through it. And now the presentation isn't working because, you know, that's how things go. Give me a second. Oh, I lost the internet connection, sorry. Okay, while it's loading, I'll give you the background, my background. So I graduated from Purdue in 2014 with a BS in electrical engineering. And after that, I applied to as many jobs as I possibly could and got a couple of them, but didn't want to do any of them. And one day Tesla found me on LinkedIn, and which was kind of like a dream come true because that was my dream company, right? And so Tesla finds me on the internet, and I ended up getting hired into the passive safety engineering team, where on the passive safety team, they deal with crash, vehicle restraints, and the sensing systems like in regards to that. And so what I started doing was like integration type work. And then within that integration work, I was basically trying to integrate sensing systems within this restraint control module to ensure that when in the event of a crash, all the sensors actuated, all the airbags deployed, and stuff like that. Again, this is taking a little bit longer to display, but I wanted to show you guys some cool stuff. But I have a backup presentation because you never know how this stuff goes. Yeah, it's just the AT&T Wi-Fi.
Yep, that's it, right there.
Yeah.
Yep,
It's connected, however, let's see, the presentation is not loading. But it's okay. I have this backup one.
Okay.
Yeah, it's all good.
All right then.
I'll just use that. Let's see, laptop. All right, awesome. So after I started at Tesla, one thing I have to say, and this is one of the least favorite parts of my presentation, is the disclosure, where I'm not allowed to share too many details. I can share everything that's in the patent, general technical principles, and information that's public about Tesla, but I can't tell you certain specifics about the circuit design and what makes it like unique in that sense, because that's proprietary. So that's just like the little caveat. So this is just the overview of how I want to go through the conversation today. I'll give you my background in a little bit more detail. I'll tell you the project background and how it kind of came to be, the system architecture and the key design elements, and then conclusions and kind of final thoughts that I have from this project. So like I said, BSEE 2014, when I was at Purdue, I was involved with NSBE, the National Society of Black Engineers, and MEP, the Minority Engineering Program. I had a few co-ops and a couple internships while I was here. I co-opted at Marathon and then Toyota, and I interned at Shell and Chrysler. If you guys notice the trends, I did 2 oil companies and then 2 automotive companies. I did the oil companies because I had this very altruistic thought that maybe, oil and gas will be sustainable. They're going to try to do something good for the world. And I don't want to share what I think about that, but I switched over to automotive because I was like, maybe they're going to actually try. And then ultimately discovered Tesla. So that was really cool. And I did a few study abroads when I was here. I studied in Italy, China, and Ghana, where I actually did my senior design out of Ghana. And then I was involved in EPICS my freshman and super senior year. And again, I started in Tesla in 2014. So my role at Tesla was really unique in the sense of what Tesla does is they basically leave it open-ended and allow for you to essentially create your own role. So what that means is you kind of come in on a team and you're supporting different initiatives and activities, and then ultimately you kind of have to piece together and say, hey, there's a deficit of action being taken in this regard. Let me spearhead that, or hey, I want to do this thing over there. So what I ended up doing was proposing my job as far as occupant sensing. I said, hey, you guys don't have any dedicated resources looking at like sensing detection inside the vehicle. Can I look at that? And they're like, sure. So that was a really cool win. And so basically for the Model 3, I developed the occupant classification system, which is what this patent is about. And what that consisted of was first designing or defining the system level architecture, the different sensors that I'm going to go through in a minute, leading the mechanical design of the sensors and the packaging of the module, and then testing and the validation, so defining what tests and needed to be executed and supporting all of those procedures, reviewing the results, processing the results. Additionally, I had the opportunity to develop all the system level logic and validating all the firmware. So I didn't write the firmware myself. I'm not really a coder, but I had a firmware engineer help me, and he basically wrote the code. And then what I would do is I would create the system logic. Once he wrote the code, I would validate against my specs. And then I would help, the last couple of things I helped with was material bring up. So that was like the supply chain, which is one thing we don't really learn in school, but that's everything that like you can, once you prototype something once, then you have to make like 500,000 of them a year. There's an entire process that's involved with that. So you have to make sure you get, for me, I had to make sure I got automotive grade parts. I had to make sure I had all of the companies or suppliers for the raw components, and I'll go through the raw components list too, and make sure that they could not only source those materials, but also build to the specifications that I outlined. And then the same, on the other side of that, I also had to make sure that they can manufacture and test that these are functioning as intended. So I had to develop manufacturing testers that validated that the sensors and the system was working as intended. And then the last part was my support, obviously, on the electrical design for both the schematics and the layout. So a little bit about the project background and context. So why is OCS needed? And really it should be a pre-slide is what is OCS? So OCS is Occupant Classification System. It's essentially what's required in North American cars to be able to sell them. And what it does is in the front passenger seat, it determines the presence or lack thereof of presence of an adult occupant. And it controls essentially the front airbag and then the side airbag. So again, it's legally required by this regulation FMVSS 208, and it's to ensure, a small female adult, which is essentially a 5 foot tall woman, or really a person 5 feet and 100 pounds and above, gets an airbag. And then conversely, it also it ensures that a child seat does not get an airbag, because if a child seat gets an airbag, it would actually be more harm than good. And so this OCS design was unique in the sense that traditionally you have this really high performing airbag, meaning that it can comply in different scenarios. It can deploy in any situation and not produce significant harm to different occupants. However, there's a huge constraint in Model 3, which caused the front passenger airbag to actually be a lower performing one necessitating the occupant classification system to be a higher one. So essentially the way I try to think about it is like, FMVSS 208 is like this 100-page document that I had to read. You don't have to read it, but I chose to read it. And basically it tells you how you can go about creating your frontal crash safety systems. So fundamentally, if you have a really good airbag, you can have a simple sensing solution. But if you have a not really good airbag, you have to have a higher version of sensing. So that was kind of the balancing act that we had to straddle. And so I want to share a couple visuals to show how difficult it was for the airbag team to create this system. So this is why I really wanted the internet, because I wanted to show you guys crashes. If it works. No, it's not working, unfortunately. What does that say? No. I really want to show you this crash. Let me see.
Go ahead. Yep.
Oh, it's because I'm still on this one.
Yeah.
Okay, so this one's loaded up,
Excellent.
but it's still not fully loaded. I can also use my phone. Do the Wi-Fi tether. That's not an issue.
Okay.
Yeah, I'll just use my phone. That should be able to do it.
This adapter.
Oh no, I don't.
Oh,
Yeah, the adapter's fine.
excellent.
Let's see. Refresh. All right. Yep, it's loading.
There we go.
So what's really unique about Tesla's overall is that we really prioritize the highest safety rating in any category, in every market. So it's not that it's just like an electric car that's really cool and has really good performance as far as driving or self-driving. We try to make the best thing in every single element that we possibly can. So safety is like our top priority. So in this crash, what you're basically seeing here is a 40 mile per hour frontal crash, which is basically you crash the car straight on 40 miles an hour, testing both occupants in the driver's seat and the passenger seat. And the intent is to understand, let me go back actually, so you guys can kind of look at it in more detail. But the intent is to understand, is the occupant, I'll pause it there, is the occupant's head being inserted at the right place at the right time? And this is on the order of like tens of milliseconds. So, I mean, a crash happens and we have these front accelerometer sensors and pressure sensors in the B-pillar that help detect that the event occurred. And then we have to make a decision. Do we deploy an airbag? Which airbag do we deploy? And then when do we deploy it? So it's a very quick series of computations in order to determine the airbag timing and the airbag type. So for this case, we see that it is a 5th percentile female occupant, which is determined by my system. And then based on that, we say we want to give a soft airbag. So a soft airbag essentially means it doesn't fully inflate and it has a vent on the side to ensure that it deflates so it's not completely stiff. And so one of the challenges, going on to the next slide, one of the challenges that was imposed was, how do you protect a 5th percentile female occupant and then also protect a child at the same time with this interior design? So at the surface, it looks like this is a really cool system aesthetically, but it really imposes a huge challenge because the airbag resides in the instrument panel in this region where my mouse is. And so it would have to project out from there and then be fully inflated within 25 milliseconds after the crash event is detected. Not only that, that's in the scenario with the 5th percentile female. On the other end, it has to be able to protect or not injure a 3 or 6-year-old if they were in close proximity to that airbag. So that's what makes it really difficult. So since it was further back, you actually needed more energy to deploy that airbag to get to the same distance. So if you imagine that you're 100 millimeters, actually it was 200 millimeters further back, but you only have the same amount of time, you need to get there faster, so you're going to have a harder airbag. So that's where they were trying to figure out unique ways to design the airbag, but it actually took them 2 years after the start of production, which was 2017. They just achieved it like 2-3 months ago, but it took them 2 years to develop an airbag that could conform to this interior design. So the high-level timeline of the Model 3 OCS development was, I told you I supported the integration activities for my first year, where essentially they were like supplier-based systems. I don't want to mention the supplier name, but basically I would take what we call off-the-shelf parts, and they were basically already designed systems, and I just had to integrate them and optimize them for whatever environment they were in. And so during that time, I kind of discovered some optimal points within it, and I realized that maybe we could achieve like a higher resolution sensing system. So that's when I proposed the research in 2015. And then I was able to develop my first proof of concept of the sensing architecture in early February. And then after that, I was able to present, I had to present to every manager. This is how Tesla works too. I had to present to my manager's manager, who was a director, that manager, which was a VP, and then ultimately I had to present to Elon this sensing technology. And that was a pretty intense meeting, I'm not gonna lie. But it was about, so the sensor is embedded in the seats, and it was really cool because there was about 15 people in the room, and everyone's going over the parts in their design, so the different materials that we're using in the seats, the structure of the seat frame, things like that. And then it comes to my part, and I present on it. I had one slide, and I had 3 minutes, and I had to like summarize the entire system to him. And this is actually, I wanted to jump ahead. This is actually the slide that I presented to him to explain how the system would work. So essentially, you have these different test modes: empty seat, objects in the seat, child in a seat, in a child seat, or a child standing, either a 3 or 6-year-old, and then the different adult occupants. And then basically I was trying to highlight here in the Model S and X design, there's a gray zone for the 3 and the 6-year-old, where that means the airbag may or may not deploy. It was undefined essentially. But in the system that I was designing, I was saying I can guarantee that we can inhibit the airbag, therefore making it safer for the 3 and 6-year-olds so they're not being injured by the airbag. And so the way I chose to do that was by using an electrode sandwich, a self-capacitance sensor in the back, and a self-capacitance sensor in the cushion. And so let me jump back to this slide. Basically, this is an image that I pulled from the patent, but it basically shows you the suppression zone, the gray zone, and then the must deploy zone, which is where the 5th percentile female occupant was. So from understanding what the legal requirements were, I was able to suggest this different sensing inputs. So this is kind of what the seat looked like. Actually, this is the Model 3 seat. So you would have this sensor down here, which is a sandwich, which is just a parallel plate capacitor, and I'll go into that in a moment. And then you have these two sensors here on the cushion, on the surface, right below the trim, both on the cushion and on the seat back. That goes into a controller that we designed, and then that controller measures the capacitance on each one of those lines, computes the classification, outputs that on a digital communication protocol called CAN, Controller Area Network. Out of curiosity, anybody heard of that? That's pretty good. So we use CAN to communicate from board to board within the car, and then that goes to the airbag controller, which in the event of a crash will deploy or not deploy accordingly. So now I want to get into some of the key design elements and challenges. So the sensing trace, I would say this was my favorite part of the design. So the sensing trace was integrated within the heater mat trace, and it was embedded under the trim to determine the occupant presence and the E-field perturbing, and I'll have an image for that too. And so basically what was happening was we have two traces. We have the outside trace, which is the heater mat, and then we have an inside trace, which was a sensor trace. So the way that the heater mat was connected on the circuit was one side was connected to a high side driver, which was just a switch that would drive a high amount of current through it, and then the other side was connected to ground. And then the sensor was a single-ended electrode on my system that would measure the electric field lines from the sense line to the heater mat. And not only that, it would also measure the impact of the presence of an occupant. And I have an image that displays that here. So fundamentally, you have your E-field lines coming from the driven line here being the sense line, and then the receive line, which would either be like a ground or your return electrode. In our system design, it was a ground. And by the presence, and I'm using a touch because it's the same technology that's in like a touch phone, but the presence of a finger or the presence of a person has some impedance to ground, which is described here as C of G. And so that adds capacitance onto the line. So if you imagine capacitors in parallel, they add like resistors in series, right? So we have Cx plus Cg, which would give us the total capacitance on that line. And one of the challenges was, if you think about this stack up, and this is one of the images that I couldn't show, I can show this high-level version of it, but I can't show the actual image of it. So when I was designing the system, I had to determine the location of each sensor. So going top down in the stack up, we had the seat trim, and below the trim were the sensing traces and the heater mat traces. So the heater mat and sensing traces were embedded directly underneath the trim about 8 millimeters away, only through a small plus pad. And so the reason I wanted it to be as close as possible was to ensure the highest capacitance. And if you guys remember our capacitance equation and relationship, it's inversely proportional to the distance. So the closer it is, the higher the capacitance is going to be. So that's why I ensured that the self-capacitance was as close as possible to the occupant. Then we had the main seat foam, and then we had what I call my sandwich sensor. I call it a sandwich because it's just like a stack up of plastics, and if you look at it, it actually kind of looks like a sandwich. But it's basically this material list here. So there's 1 millimeter of PET, which is essentially a plastic, some adhesives, a copper, which is the conductive portion of it, a dielectric foam, which was like specifically selected to ensure that I achieve the optimal or the maximum deflection with the same load applied, another layer of copper, and another layer of PET. So now going back to this one, you can see that that was embedded between the seat foam and then the spring mat. And so the spring mat was essentially the area on the seat frame that allows the seat to deflect when someone sits there, so it's not like a stiff bottom that you're sitting on. So this is the, again, high-level version of how I measured the capacitance with this circuit called a relaxation oscillator. Essentially what the relaxation oscillator does is, if you have your non-inverting terminal, it'll start at some potential and then it'll trigger the output, because if this is at some threshold, we'll say it's initialized as ground. So it's at some potential here. There's going to be noise. Again, we're talking about non-ideal cases, right? In an ideal case, it's like, how does this thing start? But in a non-ideal case, you have to inject something for it to start. But in this case, it's going to start on its own, because the non-inverting and the inverting terminal will never perfectly be the same. So once you see a difference there, that'll change the V out to be up, causing this voltage, we'll call it, it's a 5-volt system. So we now have 5 volts on this line. And so this voltage of 5 volts is going to go through this R1 and charge your C until it reaches this threshold point, which is the potential here. And so if you imagine this V out here, and we'll assume R2 and R3 are the same. So the voltage divider here is just going to have half of 5 volts is just 2.5 volts. So once this system reaches 2.5 volts here, that's going to trigger the V out to go back down, therefore discharging this capacitor. So we're just charging, discharging based on the R and C in this circuit. So yeah, I just provide a little bit more detail here. And so the ways that I improved upon just like the fundamental method of the relaxation oscillator was I had to use COG caps. So there's a specific type of ceramic cap that have the lowest temperature coefficient. So they're 30 ppm. So over temperature, they're pretty well contained. And then I had to reduce my R, or optimize my R, to increase the current that goes through that capacitor. And the reason that I wanted to increase the current was to ensure that I wasn't having too much noise to impact it. So essentially, I had a major issue that I'll get into in a moment, where noise currents would impact the system, because I was initially drawing microamps, like tens of microamps, because I was using R1 of 50K and I was using a C of 100 puff. So it was drawing microamps, but milliamps of noise would completely drown out my signal, making it completely useless. And then I had to use a high accuracy resistor. So in the next page, I'm going to show you the equation for how I calculate the capacitance. But the series resistor of this cap, its measurement error would impose significant error overall in the capacitance frequency measurement. And then the last part was I used a comparator instead of an op amp to ensure like the fastest slew rate possible, which is essentially like the digital changing from 0 to 5 volts. So I didn't want it to like slowly ramp up to 5. I wanted to like shoot to 5 volts as fast as possible. So fundamentally, here's the equation that we use to calculate the capacitance. So the F here is frequency, and it's 1 over KRC, where the K is just a constant. I didn't think that was important. And then R here is just the series resistor, and then C is either the parallel plate capacitor, C mutual, or C self. And so any errors imposed by R1 will be seen in my frequency measurement. So I had to use a high resolution, low ppm resistor here. And so like a typical, like if you're buying resistors in the bulk, like millions of resistors a year, they're going to cost like a fraction of a penny, like 0.001 cents. But the resistor that I had to use costs 5 cents. So it's pretty significant in my BOM cost, but that was imperative to ensure that the frequency measurement was very accurate. So that was actually one of the most expensive components on the board, because I used 10 of them. So it cost me 50 cents to just use resistors. Kind of ridiculous. And then we have the equation for the parallel plate capacitor, which you guys all know: epsilon times epsilon naught times area divided by distance. And then we have the relationships for the self-capacitance being inversely proportional to the impedance and directly proportional to the area, and again, inversely proportional to the distance. So when I was thinking about this design, these were essentially the cornerstones of what I would reference within all my design decisions. So for one, I described the importance of R1 and had to specify that. The other thing that I had to specify was the sensing area, right? The larger the area, the more capacitance that I get. But not only that, I can get bigger wins if I focus on the distance, right? So the distance between those parallel plate capacitors, the smaller the better. So I looked for in the market the smallest piece of foam, the thinnest foam that I can have, because that would give me the highest initial capacitance. And then I would also want the softest foam available. And so I'll go into that now. So one of the things was I had to do a pressure map assessment where I had a major issue where in the initial design, I only had I forget how much sensing area, but I had this 120,000 square millimeter area. And so it was essentially a snapshot of the load imposed into the seat. And so the challenge there was, in the cases of a 5th percentile female, which is again 100 pounds, and a 50th percentile male, which is about 170 pounds, there was a condition where the legs were extended, where if we look at the Model 3 OCS prototype, the Model 3 can't easily separate the 5th percentile from the 50th percentile. And that's because the snapshot is so small, right? The 5th imposes a lot of weight in this concentrated region, whereas the 50th, being a larger occupant, distributes more weight throughout the seat. And so to show this a little bit better and kind of walk you through what we're seeing here, this is just like each leg, and then if you see like a crease there, that's essentially a trench in the seat. And then if you look here on the sides, there's additional weight there. That's like the side bolsters that a lot of people put weight into, but like a smaller occupant isn't going to be putting weight inside of the cushion bolsters, as opposed to like a 95th percentile male, which is 210 pounds or greater. They're going to be imposing weight on a larger area just because they're a larger person. So one of the key design challenges I had here was trying to optimize the sensing area for cost. So I couldn't use like the full area that we see here, which is just like this pressure map. So I used this entire pressure map. It's a high resolution. It's like a $100,000 piece of equipment that gives you the entire distribution of the load imposed into the seat. I use that to assess and say like, these are the regions that I want to have my sensor. And ideally, the lower you are in the structure of the seat design, the more weight that you'd be able to measure or infer. So if I was as high up as possible, I wouldn't be able to see all the load imposed into the seat. And in fact, I would be kind of disillusioned by the point loading. So I wanted to be lower where again, if you think back to this slide, I wanted to be lower through the seat foam where the weight would dissipate through and then have to go through my sandwich sensor and then through to the spring mat. So the challenge here was I was going to lose some of the load applied onto the seat from the bleed off on either side of the foam, but I wanted to increase the size, but I was limited because I had a budget of $45 for the system. And so if I just like blew that, I kind of blew the budget on the sandwich, but I had to optimize the sensor design to ensure that it was large enough that I'm able to properly resolve a 1/5 versus a 50th, but also didn't cost too much, right? It didn't break the budget. So that's when I essentially proposed this sensing area that you see here, which is the lighter blue, and I use that as a benchmark from the Model X design, which is a bladder-based weight sensor. So I used that and said, okay, this is sufficient area coverage. I want to use this much coverage in my design to ensure that I can separate or resolve these two classes. So once we look at this image, you can see that this larger snapshot shows 77 pounds imposed in that range, and then it shows 100 pounds imposed for the 50th. And so basically we're saying now I can resolve a 1/5 versus a 50th by their weight. The other part, and this one took months, was finding a foam that had the proper compression force deflection curve, a CFD. And so a CFD curve basically tells you your stress versus strain. And this curve was really difficult to understand at first. It was kind of counterintuitive, but like if you're looking at this one, I'm curious, like at first glance, can you tell which foam is softer? All right, so yeah, and that's one of the challenges. Like as an EE, we think of circuits all the time, and then we get a mechanical problem. We're just like, yeah, you got me. But I had learned, through this project about how the CFD curve works. But essentially, what we're looking at is the stress on the y-axis, which is the pressure, and then the strain, which is the percentage change from the original state. So if we're at 0, 0, that means there's no pressure, there's no strain being applied here. There's also no pressure. So it's at its ideal state of just 0 change, right? So as we can increase strain, right, we're reducing the overall distance. And then at the same time, to decrease that distance, you need to apply pressure to it. So we're applying pressure, which is the y-axis here. So that means that I put this black line here. If we're applying 0.15 newtons per square millimeter of pressure, and then this orange one only deflects like 40%, but for that same amount of pressure, this blue one deflects like 75%. That means the blue one's softer, right? So I selected the blue one, and then from there, I was able to show, by choosing the blue one, I'm able to see a greater change in capacitance, right? So from my initial state to like a given load applied, I want to have as much deflection as possible without saturating the system, right? Because I didn't want to apply like a little bit of load and then it just squishes, and then I'm like, well, I don't know how much load is actually applied. So that's why I selected this foam, because it gave me that the right amount of deflection for the load applied, but it also gave me a significant capacitance change, where I walked through the equation here with you guys, where again, assuming the same pressure applied, how is the deflection different? So for an example 1, for a softer foam, it deflects 50%, so the distance will be 0.5 d, whereas in the other one, it deflects 0.75. So what you end up seeing is, once you extract that 1/2 out, you see that this one is two times the empty capacitance, where this one's only 4/3 times the empty capacitance. Right, so I wanted to get as much change in the C as possible. So the next part was creating the manufacturing testers. So there's a seat calibration station that I created at our seat plant, which is in California as well. We manufactured both the seats and the vehicle like in California and Fremont area. And so it's like really cool because they're only like a mile apart. And a lot of times you go from one place to another to like debug issues on the line. So the reason for seat calibration is to normalize all of my parameters, right? There's part-to-part variation for the resistors, the onboard capacitors, the entire circuit. There's also a huge part-to-part variation on the sandwich design and on the sensor design. So the only way to normalize my metrics was to calibrate it out. And so what I did was I measured the empty conditions for all the sensors to essentially calibrate out the passive components on the board and then all of the sensors baseline. But also that CFD curve I showed you where we looked at the blue one, that's just the nominal curve, but we can't guarantee that that curve will always be the same, right? There's going to be part-to-part variation. And so based on that variation, I needed to calibrate how much load it sees for a given weight. And so what I essentially did was we built a manufacturing tester with a gantry with a B-form on it. And B-form is just short for butt form. That's all it is. And so you can see the B-form here. And so the B-form goes down. It has 2 load cells, and it applies a predefined amount of weight on the seat, waits until that weight settles, and then the sensor reads it and says, okay, this is what I see as 60 pounds, and then it stores that into the calibration parameters. And so basically what we're looking at here is then I normalize all of the plots or all of the seats, and then I've collected the data between empty, a 6-year-old, a 5th percentile female, and a 50th percentile male. And so on the x-axis, we're looking at the cushion mutual frequency, and then on the y-axis, we're looking at the cushion self-frequency. So if you recall, again, from the equation, the frequency is inversely proportional to the capacitance. So as we increase in weight, we're decreasing in our frequency because we're increasing in our capacitance. Again, that's kind of confusing, so let me go back. So if we're here and we say we increase our capacitance, so that goes up, so that causes our frequency to go down, right? So that's essentially what I'm saying there. And again, that's what this plot corroborates, where in an empty condition, the different seats sit around here, but once you apply weight, the more weight you apply, again on the x-axis, the lower the frequency goes. Similarly, for our cushion self-capacitance sensor, the lower the frequency, the more self-capacitance coupling that's occurring. So in an empty condition, it sits here, but as a larger occupant or someone who has a tighter coupling to ground sits on the seat, that will increase their capacitance. So based on this, I created, this is the initial 2D plot, but we also have a third parameter that we're looking into. And so I was able to define the initial classification zones. So basically the gray is the empty region, the red is a inhibit region, and then the blue is the small occupant, and then the green is the large occupant. So you can see that the large occupant kind of bleeds into the blue. And so that's actually okay for this system design. So what we're really trying to prove fundamentally with this system was ensuring that we can always separate the red X's from the yellow circles, which is just a small child versus a small adult. And so we can confidently do that. But the other piece that actually enhances our ability to separate this is, I'm actually going to come back to that, is our 3-dimensional plot. So I used MATLAB to generate this and basically just did some analysis where I computed the planes ideal to like bisect through these to ensure that complete separation occurs between the green and the red. And then I try to optimize for the amount of separation between the 5th, which is the red, and then the black. being the 50ths. So we created these two planes to separate the different classifications, and then we implemented this in the firmware. So another piece within the firmware that I wanted to discuss was the dynamic performance. So I don't know if you guys ever noticed, most people don't. In the front passenger seat, there's that airbag light that turns on and off depending on like who's in the seat or if you're moving or not. And so one of the things that I tested was the dynamic performance to ensure that the classification isn't changing excessively within the design. So I didn't want it to change if you're like leaning over, unless you've leaned over for too long, or if you like reach in the back seat, something like that. So I had to apply some logic to the system. So here is one of the test designs that I had where it is a barn circle. And so a barn circle is basically like, if you look at this intersection here on the highway, it's essentially the profile of when you're getting onto the highway, right? So when you're getting onto the highway, what happens normally is you kind of offload some of your weight and you lean either into the door or you lean into the center console. So you're not putting all of your weight in the seat. And then at the same time, you may not be making as much contact. Your area of contact may be reduced as well. So what I'm showing here is that in the event, the occupant goes from large to small to inhibit for a few seconds, and then they trickle back after the event is over. And so, and you can see the increases of each one of the sensors. So the seat back being, I would say, the more significant change, you can see that in the event of the turn, they're kind of leaning forward out of the seat for several seconds, where in an unfiltered design, it would be an incorrect classification. So that's where I went in to basically say, not only low pass filter the classification, but also add logic where, okay, if it's in these conditions where the buckle is latched or the door is closed or that state has been consistent for the last minute, hold that unless we know there should be a classification change. So essentially just adding hysteresis to the system so we're not excessively changing classification. And so then one of the biggest challenges that I had, and I did not resolve this in its entirety until like last month, and this was really hard, but this was a noise susceptibility issue where you have two different supplies. I had a dirty power supply, which was essentially a wall wart. Just like regular, like a electronic device, you can cut it and change it into like a 12 volt DC source. And those aren't always clean. So what occurred here was it would make a very noisy measurement for my system. But then I tried to like validate and say, well, like our batteries in our cars that apply that 12 volts, they're clean, so it should be fine. But then it's like you can't assume there's no noise on a 12 volt supply. Even though it's a DC line, there will be noise coupling in because we have all these different sources from CAN to like high frequency radar measurements and stuff like that. So noise will couple into the line and impact your measurement. So I had to design some noise immunity into the system. And again, I can't show you all the details on that, but essentially what I do is I have these different high frequency caps where I use different capacitors. And let me show you this one. I use different capacitors where the capacitor essentially acts as a shunt element, having that high frequency noise travel through there instead of entering the circuit. So on the left, I show here the impedance versus frequency. And you can see that, again, a capacitor in an ideal case is 1 over j omega c. And you can see that performance here. But then there's a point in every capacitor's life that it becomes inductive. So at this point, it starts increasing, and so it's not going to be as effective. So this is where I use, in this example, this looks like 100 picofarad cap, and it has a self-resonance frequency of about 800 megahertz. So I use that plus like a 1 nano, a 10 nano, and then a 1 microfarad cap and create a network where all of the noise wants to shunt through there. But also on the other end, I want to make a series element that looks into the device for a ferrite, which is essentially like an inductor. And that increases as j omega L. But again, not everything's always going to be ideal, so there's a dropout in its performance. And so I selected this part here, this MMZ 1608 S202A, because that had the highest impedance around my noise susceptibility range. And so my system was the most susceptible around 20 to 30 megahertz. So that's going to be around here. And so all these other ferrites do not perform as well as this one. So I wanted to basically say, I don't want anything to come into this network. So this has a high impedance at that frequency. And so instead of wanting to come through this ferrite, the noise currents are going to want to go through the lower impedance path, which again, this one's going to be on the order of tens of ohms. So the majority of the noise will go into that. So some of my conclusions or final regards with this design was this was a really big development. So I proposed this design in around 2015, and it was crazy because I was like an associate engineer at the time, like I was just a new grad, and I basically said, hey guys, we should make this entire system, and they're like, okay, sure. And they kind of gave me the reins to do that, and I thought that was kind of bizarre, but it was really cool because in that process, like I was able to build a team. So I was a lead engineer, even though I was like very young in the design, but I understood the fundamental pieces that are described here, and those were the guiding pieces to make the decisions for the design. And so it was our first in-house safety critical ECU that we've developed. So this was happening for like passive safety. So none of our other crash sensors or elements are done in-house. This was like our first attempt at doing that. So it was a really big moment, and it was also big because it enabled us to launch Model 3. And so like I was saying before, it was either the airbag had to comply or the system or a sensing system had to come in and essentially save the day. So if they essentially did not and was not going to compromise on that instrument panel design, so they needed a way to ensure that we can still legally sell cars. And so I was able to come in, we were able to create this system. So that was really cool. And then another thing I like about the design is actually modular. So if you guys think about how I had the 3D plot, if you take like a 2D cross section, you can say, okay, can I determine the classification just from that 2D cross section? And yes, you can. So what I did was I removed the sandwich, which was like the $30 piece in the system, and I removed the sandwich, reducing the price significantly, and said, I can still give you really good classification. And so in corporate, they like cost savings. So this was like a really big deal when I was able to propose this. And so I was able to, we're actually implementing this change in the next few months. I'm really excited about it. And so now the resolution that the sensor is gonna have is, even though it can separate the red from the black, I only have to separate what I have circled here from the black. So you can see that that's very easily attainable with this 2D cross section. Some of the lessons learned that I learned in this project, this was the first thing that I've ever seen like through into production. So this is the first thing I've ever put into production. So that was a really, really difficult feat to achieve. But one thing I learned was like the framework in which we design is you want to prototype as early as possible and try to break it. Don't try to make it work, try to break it. And so like you'll make it work, that's the easy part, but then figuring out how to ensure that it's robust, that's the hard part, because in this system, again, in ideal conditions, it worked perfectly, but in the presence of noise, in the presence of temperature, in the presence of part-to-part variation, then the system gets harder to define and make consistent. So you want to try to break it in as many different ways as possible. Another thing I learned was any design element that is arbitrarily defined is probably wrong. And so what I mean by that is, if we go back, for example, to this page, right? If I selected the R to just be 10 ohms, and you're like, oh, why'd you select 10 ohms? It was a number. It's like, well, there's no rationale behind that decision. So that actually initially was an arbitrarily defined element of 50 kilo ohms, and that actually hurt us because it was too low a current draw. And it's like, why did you select that? I don't know, I just thought I should use that value. And so then we had to change the resistance value to increase the current draw, and so now it was defined. So there were some things, certain elements within the design I discovered that were, since they were arbitrarily defined, it actually kind of bit us down the line. So you want to avoid arbitrarily defining things and kind of scrutinizing your design and say, okay, why did I select this? Or can I optimize this or can I make this better by actually creating the rationale behind it. So the next thing I have that I learned was that step one isn't to innovate. I think a lot of times we want to like just go straight out the gate and just like make something brand new. But I'm stealing this quote from someone, but I heard copy paste then innovate. And essentially what that means is instead of just taking or creating something out of thin air, what you do is kind of like what musicians do in the sense of you find inspiration or you find pieces and you integrate them together. So this design isn't unique in and of itself, in my opinion, but what I did was I took a known circuit, a relaxation oscillator. I took known things and integrated that, right? Weight sensing, that's not necessarily new. Self-capacitance sensing isn't necessarily new. By combining it into this system, that makes it unique, right? And so basically I was drawing inspiration, and in that way I was able to innovate a system. The next thing is knowing your constraints. So this one's big because I think currently we emphasize at work a little bit too much of the cost, but I think within your design you have like these different physical, mechanical constraints, you have component constraints, and you have resource constraints, where resources is anything from people to like raw materials. And so one of the biggest constraints that we had in this design was the foam element. So this was actually the softest production or automotive grade foam that we could find, and it kind of sucks because there's softer foams out there for sure, but to get a foam that met all of our other criteria was really difficult. And then being able to get the performance out of it, we still had to stretch the design in order to achieve that. So knowing your constraints kind of enables you to make the right decisions within your design. So it's kind of like that same thing where it prevents you from like that arbitration, but it also limits you as far as what you're able to do. So you're kind of like creating this bounding box for your design. And then the last thing I want to share, because I, over the last year, have done over 500 noise immunity tests. And so each test takes about 15 minutes. And then in between each test, I would change at least one component on the board. So, and I've done like 500 of those. Electrical noise sucks, and I just really want to emphasize this now, and can kill the reliability of a product. I use different tools to help model it, like Spice, to help model my noise networks. But one thing about noise is that it cannot easily be modeled all the time, right? You can impose a model and say if you have a noise profile that looks like this, but real world noise does not care about your idealities at all. And so that's really what makes the design difficult. But yeah, I would say electrical noise sucks, so look out for that. All right, thank you. You guys have any questions? Yes?
What countries did you use to get the data for the average human weights?
Oh, so let me jump back here. So the weights are actually defined within the regulation as well. So FMVSS, literally in this section, tells you each weight category, or each occupant category, their weight and size. And so I just pulled that information from the document. It's actually based on like mid-80s census data. So like that's obviously different now. It says that the average male height is 5'8" and their weight is 170 pounds. I'm pretty sure that's different today. I don't know, but yeah, it's pretty interesting. Yeah, man.
My other question was, you mentioned noise interference like radar.
Yeah.
Are you specifically meaning like police radar? Or?
No, I was meaning like inside the vehicle, right? Even though the radar is projecting inside, assuming like they don't do their job, there's what's called like, there's noise immunity and then there's emissions. So every module is going to emit noise, and so that noise emissions can couple onto a line. So radar is literally just noise emissions, right? That's how it operates. So it's basically projecting this high frequency and then reading it back, but that's all emissions. So if that couples into either the power line or a communication line and goes downstream to like my device, that can affect my measurements. Okay. Yeah. Or I guess the other piece of that, which is what we dealt with, and we had an issue in LA where the autopilot would disable. erroneously because there was a military radar that was like right around LAX. And so every time it points at a Tesla, the autopilot is just like, ah, and it was just spaz, and it was really crazy. And so basically that was happening because there wasn't proper ground loops, right? So you want to have like the best grounding paths for that noise current to go through. And so essentially the enclosure was a metal box, but it wasn't actually connected. It was only connected through like one point instead of being connected to like a significant area to reduce that impedance for the noise current to go through. So they had to add a gasket in between the enclosure and then the connector. So the connector would see the noise, and then it would go onto that gasket and then go onto the entire enclosure to dissipate the noise in the event that that radar points at it. So it's very like nuanced things like that where you don't see it until you're in the field, and then all of a sudden the noise hits you. Yeah. Yeah.
You talked about the difficulty in choosing the foam. Did you have any challenges working with like designers in terms of the aesthetic or the comfort and that kind of stuff? Did those play into your design decisions?
That did not play into my design decisions for the sandwich as far as the aesthetics, because this is a B surface. So A surface is essentially above, this is what you see in the car, and then the B surface is below what you don't see. So since this was below what you see, no one really cared about how it looked, but it still had to like meet a certain standard. The major things that impacted the comfort was, again, ensuring that things weren't arbitrarily defined. I wanted to originally make this plastic PET like 3 millimeters, and I was like, I have no idea why I want to do that, but I'm just going to make it 3 millimeters. And what that ended up doing was causing a comfort issue, right? Because this sensor actually has to deflect and move with the spring mat, so I had to reduce it to ensure that we get sufficient deflection and essentially the occupant doesn't feel it. So that was the only piece that really affected comfort. And then as far as like the sensing traces, they're extremely thin wires anyway, so, and they're embedded underneath a plus pad, so an occupant couldn't feel that. Yes, sir?
The materials like foam tend to age and get flat.
Yes.
How do you look at your design?
That's a great question. So within the reliability, what we did was we did an aging profile. So there's actually a break-in period of the foam, and so it would take like on normal usage about a year to get to the break-in performance of the system, but that was kind of excessive, and it was difficult for us to create a model for that like trajectory because we couldn't impose how it was going to initially be aged. So what we did was we cured the foam, so we would bake the foam for 18 hours to basically make it reach its like steady state performance. And so once you bake it, it reaches its steady state, and then it's going to start to trail off after about 5-6 years. And so to get that degradation profile, what we did was we have a chamber that is at, what is it? I think it was 95C for 8 days. So 95C for 8 days nonstop simulates 10 years of aging. So what we did was we put the foam or the sensors in the chamber, and then we would take it out every once in a while, every like day, and basically see the aging and degradation profile of the foam. And so then we can implement that in firmware once we created a model. Yes, sir.
Did you have any mentoring resources while you were going through this, or were you pretty much on your own?
That's a great question. It was crazy. We hired another engineer. So I started out like, again, as an associate engineer, and through this project, I essentially reached staff engineer, but we hired a staff engineer who was what I would say the EE expert, and really the guy who came up with the relaxation oscillator. And so we hired him in as like EE support, but as far as like all the other support, basically what my job was to just pull different resources from different teams. So I basically led the team with a mechanical engineer, electrical engineer, firmware engineer, 3 test engineers, and then an integration engineer. And then I had them do a lot of the work in the sense of like executing their expertise, and then I was leading all of the efforts. Yes?
So you said that you presented, like, you proposed this, like, in 2015?
16.
2016?
Yeah, because it went into production in 17.
Over 3 years to, like, go this whole thing.
So let me go back to the timeline. So the first proof of concept was in February 2016, but then it reached production in 2017. And so it was like a year and a half of like overall development. But even after 2017, there were still things that were like unfinished in the sense of like could be optimized. And one of the beauties about Teslas that is really our saving grace is we have over-the-air updates, right? So normally ECUs, once you validate it, it is in its state for firmware for the rest of its life, unless you take it to like a service center and they swap it or they can update it. But one thing that I didn't have was, like you said, the aging profile. So I didn't have that day one. So I still was running tests, but we said, okay, we can start production without this information and we can update it over the air. So once I was able to create that model, then we say, okay, update that over the air. I mean, we still have time because, you know, these cars have only been out for like a couple of months, right? But once it reaches that 5-year point, it's like, we need to ensure that all these cars have that aging profile firmware. So even though like it reached production in 2017, there was still some refinement within the firmware to optimize the design.
So it's like even now you're still optimizing it?
Right now, I'm not touching it. Right now, this was like the version 1 design that we put into Model 3, but I actually just finished, actually Monday, started production for this new design for the version 2, where I use a different method of measuring capacitance that's like more noise immune, because this one is still too sensitive. So I have like higher current draw and better noise immunity.
Are you looking at it like at a completely different view, or like doing something completely different than like what you do here?
No, it's essentially using the same it's same sensing modalities, but a different way of measuring that capacitance. Yeah, so the version, like I would say version 3 is changing the sensing modalities as well. And so like, without going too deep into it, like we have a selfie cam in the car. We're not allowed to use it right now, but we have selfie cam, and then there's things like nano radar, ultrasonic sensing. These are things that we're looking into for like interior sensing for occupants. Because one thing that we've struggled with really like the last like 4 years is how we integrate this design is like heavily dependent on seats and what the seat team does. And so instead of being having them be our bottleneck, we'll take the design out of the seat, put it somewhere in the cabin, and then be able to infer occupancy that way.
Are you in like more of like a project management role?
No, I'm more the lead engineer. So I still do all the technical stuff, like I analyze all the data, but at a staff engineering level, I can't be touching all of the things at the same time. So for this version 2 design, I developed the schematic and layout and everything, but then I still have to outsource essentially like all the other elements of like the mechanical pieces and stuff. Yeah. Yes.
So, when you talked about calibration, you said that obviously every component of a sensor is going to be somewhat different than a minute idle.
Yeah.
So is your calibration matrix based on, say, in terms of percentage perturbation from what you consider ideal, or how?
Yeah, so there's definitely like an acceptability limit. So it's not just like, oh, calibrate this and then it's good to go. There's an expected performance that it should see, right? So one of the issues that we had was within that foam, again, it was a soft foam, but it wasn't always soft. From part to part, different like lots of it would be stiffer. So when I did the calibration measurement from the empty to the occupied or loaded condition, if it didn't move enough, it had to be a failed unit. So we had to fail a lot of units because we had a lot of like I think it was over 1,000 sandwiches that were just below the spec.
So there was nothing like you can change in terms of other things which can make that unit actually usable? That's where we had to like reach a limit, because if it doesn't deflect enough, right? So I only see a small change of the capacitance over temperature and humidity, that noise, that's going to add like a noise floor to the measurement. So that small amount of change would be kind of eaten away with noise. So it would still fail eventually or potentially misclassify. So that's why we had to draw the line there. Yes?
Go ahead. Go ahead.
Well, I was just gonna ask. You got your E here in 2014. So, any classes that you really thought were really helpful? Like
ECE 311 is the first thing I can think of. Yeah, that's the first thing I can think of. And then 255
I think that's when we started like learning like SPICE. So I didn't show any of my SPICE models here, but I will say I was not comfortable in like creating any SPICE models when I was like in school. Like it was always awkward. And then when I like got to work, it was like, no, you got to do this every day. And I was like, ah, crap. And so that was like the hard part. So, I mean, there's a ton of resources for like LT SPICE and stuff. So I was able to like learn how to do that. And then you kind of, the cool thing, and this is what I would encourage like from ECE 255 is like, the cool thing is like, if you don't understand how a circuit works, just like throw it in SPICE and like try to figure out how it works. Because if you don't, I mean, you should know like your KVL, KCL, but like once it gets a little bit more complicated, the networks get a little bit more confusing. You're like, I'm not sure what's going on here. I don't want to like write everything out. So what we did was like we would create these models, right? Throw it in SPICE and then try to probe at different points and then kind of build that intuition, right? And I think that's really what helped us, because if we were doing the computations for everything, we'd still be working on it probably.
Actually, they changed 255. They were making it so that 255 is combined with 202 and 201. So
Oh.
it's called 2001 and 2002.
Interesting. Yeah.
2002 right now.
Okay. Yeah. So you're basically like learning all of the linear circuit design and then throwing in.
We have like projects we do in SPICE and stuff.
Actually, that makes more sense. That's good. Yeah.
It's led by Talmadge. I like him.
Nice. Yeah. Yes.
During the time that you presented your design that was approved,
Hmm.
did you actually, what was your role in getting it ready for production?
What was that?
Did you have a role in getting ready for production once you had approved your design?
Oh yeah, it was the entire like productization phase, right? So that's where I think I explained.
You probably did.
Yeah. So my role was like, essentially once we defined the system, I had to design the mechanical or get someone to like put that in the CAD and lead each one of these initiatives. But I would say like my focal point was probably within the system validation, right? Defining all of the firmware, which I didn't even go into, as far as how the system needed to properly classify, and then working on the electrical design and basically understanding what our constraints were. Because it was the electrical design that imposed like constraints on the sandwich, which was imposed by constraints on the cost and like that whole feedback. So I would say like, if I was to put it in a job title, I would say this was like a integration engineer type of role, or like a systems engineering type role, where you see things at like a holistic view, where I wasn't necessarily the like responsible EE for this. Like I didn't do the schematic for this one. I did it for the second one. So the responsible EE is responsible for the design of the schematics, ensuring that all the sims go according to plan. The layout is right in the sense of all the components are placed properly, and then that entire supply chain. But what I did was kind of dabble in each one of these facets and then supported each one of those team members there. And then after this project, I found out that I wanted to go deeper into the electrical side, and then that's when I worked on the version 2 design that we're going to start production on like next week. Yes?
So supply chain, would that just be like, could you explain more?
Yeah, supply chain is the kind of business side of it, where it's basically the process of getting the materials from point A to point B. Like the materials, what materials they are, manufacturing those materials. So we use a supplier in China, and basically what we had them do was we gave them like drawings for all of the elements. Let me find the right slide. Right, so we gave them the drawings for this sandwich, and we said we need material, this PET material that's this thick. We need an adhesive that's this thick, that also can secure like a copper to a PET, and then we need this foam, and we actually have to source that from another place. And then it's basically working on, it's the logistics of it, right? We need to work with another supplier to provide the foam to that supplier to build into this sandwich. And then once they build all of that, then we needed to ensure that we can test it and then ship it all the way over here to California, or there to California. Yeah. All right. Thank you, guys.
Thank you all for coming today.
Oh, Tesla is the place for you. It's, I would say, one of the most technically rigorous places because really